Hello, my name is Aditya, and I will be doing a presentation on dissecting click fraud autonomy in the wild, which basically is we'll be trying to uh, get a solution for click frauds, specifically for the human attack. So, the topics that we'll be covering today is first of all, we'll be seeing the the click fraud attacks and specifically the humanoid attack and what is the problem with it and what uh, currently what the industry's problem with it. And then we'll go into the old dynamic solution, which is the standard solution and why it fails regarding uh, tackling humanoid attacks. Then we look at the click fraud ecosystem as a whole, and then a motivating example of an attack, and then we propose the solution in the paper, which is the click scanner, which works in Android systems. Next, we uh, go through the flow or the workflow or the process of the click scanner solution, and then we just do some discussion and some conclusions on the click scanner solution. So, what exactly is click fraud? Basically, how uh, advertisers send ads to a project or an app. The app presents those ads to the customer or the user. The user clicks on those ads, and those ads, every time they are clicked, they generate money. I mean, you get a signal to the ad service, and you get it. What click fraud is basically uh, certain SDKs or libraries or certain fraudulent applications that generate the ad clicks automatically without any user intervention. Uh, so so basically, click frauds have resulted in huge amount of financial losses for advertisers, and uh, also around a tune of around 42 billion USDs just in 2019 alone. So now we get to the humanoid attack. Uh, Basically, this is a special kind of attack, a subset of the fake click attacks, where we try to generate clicks that are extremely similar or extremely to what a person would normally perform, but it is randomized. So the randomness of the attacks is the cause of why it is extremely hard to detect because it's similar to uh, a user clicked event. Here we also not only do randomizing the click events, but also we also randomize the time intervals and also follow the legitimate actions the real users can click. Like if there's a button that needs to do like next or close a ad or something. There is also the case that some applications could get their configurations from a remote server who which can feed them information on what to do, where to click, and what coordinates to process. So now we see what are the existing click fraud detection schemes, which can be mostly divided into two types. One is the user side detection, where a certain application or a patch is installed on the user's device to check the click patterns generated by the users. Some of the examples are ad shocks or fraud detector. But for this to work, uh, human clicks and bot-driven clicks have to be almost, there shouldn't be any inconsistencies. So where it fails is that usually attackers use the motion event dot obtain function to actually simulate the motion event, and usually the user slide detection fails to actually cover such a function. And also another failure is it has a large time overhead and cannot cover all the app's functionalities. And the second type is the ad network side detection, where we analyze the ad requests on the network server. So it's basically a server-side processing of your clicks and to check whether there's any kind of click fraud happening. So it's unusual traffic is almost simple reuse of legitimate data, and also whatever is repeated themselves in the same click stream is recognized in terms of the ads. Where it fails is it does not rely on legitimate click data streams. If the fraud does not rely on the legitimate click data streams, then it fails. And also it also fails if there's a if uh, if the attacker constructs similar data streams of that of legitimate uh, streams to fool the detector. Okay, so now we move into the proposed solution, which is called Click Scanner, which is proposed by this paper. Uh, it is specifically designed to handle the humanoid attacks. It is a lightweight static analysis framework which automatically detects these type of attacks, and basically it composed of around 4 stages. First things what we do is we try to identify the human attack and build a prototype. So basically if there's like a manipulation of the motion event object uh, for the click sequence. Second, we identify around 50 legitimate clicks and 50 illegitimate clicks, and we use that as the seed for accuracy testing. Third, we propose a very lightweight detection in the paper, propose uh, you, a data dependency graph or a DDG to extract the features that are mostly related to the attack. And to conclude, we overcome the lack of positives uh, in our test data set using veritational autoencoders to build the classifier, which is based on a one-class classification. So in this figure, we have like an overview on the mobile click ecosystem, ad ecosystem. Basically, the advertisers, they send the money and they buy ads using the ad network. The ad network actually sends an SDK to the developer to use for processing the clicks, ad clicks. Uh, so here we also have a benign developer and a fraudulent developer. Uh, the benign developer, uh, the functionalities are the same. The the clicks are registered and the ads are registered and it goes to the ad network, and the money is deposited for the developer. But what a fraudulent developer does is they use an API that generates the click frauds, and that is actually given to the ad network and subsequently to the advertisers. So this is something which happens during a normal click versus a fraudulent click. In a normal click, what is there is we use like a X and Y axis. So where we click, it generates the exact point, the X and Y axis, and it sends it to the ad network. But what a fraudulent app does is it generates the X and Y by itself without any motion by the user and sends it to the ad network by so defrauding the user. So next, what we do is we start with a motivating example and some insights regarding the example. What we're trying to do is we're conducting a preliminary study to collect several fraudulent apps towards building a click scanner beta. The click scanner beta, it monitors every invocation uh, and which generates the motion event dot obtain object, this motion event object actually triggers the dispatch touch events to that. So, so after building this seeding app using the manual verification, we establish the features. So to find the differences between both the humanoid and random attacks, we use around four distinguishing features. Uh, there are two basic ones where we randomize the coordinates and randomize the triggering time, and two advanced things where we try to mimic real actions by people, like what the logic real people would use, and also to try to get click coordinates from a remote server. So a remote server will give you the click coordinates to do the attack. Here we see a few graphs regarding the final uh, representation of the motivation example. Here we use fixed clicking, where coordinates are fixed, and they generate only on fixed events, and also replay clicking, where it replays organic click streams on the ad parameters. Here uh, we have the normal, the fixed, replay, and the humanoid. That's the attack. Uh, what we see in almost most of the graphs are the normal and humanoid are almost indistinguishable, but the fixed and replay are easy to detect. This is more uh, noticeable when you use the click time generation. I don't think you can see the graph, but the normal and the humanoid, the time frames are extremely similar, but the replay and fixed can be easily detected. So this is the result of the motivating example. So now we'll be trying to explain the entirety of the system design of QuickScanner. Uh, what we are doing in the right now in the briefest of senses, uh, we have an AP key. We're decompiling. We're trying to get relevant information and build the data dependency graph. This graph will be fed uh, in the feature extraction mode, where we'll be going through a set of features and create feature vectors. And this will be fed to the fraud detection module, where we'll be using our uh, where we'll be using a classifier based on the varitational autoencoders with a limited knowledge on fraudulent examples. So the first part of the three is the app dissecting module. Here we actually see whether the click scanner mobile ads. Sorry, if the if it's related to mobile ads, and if it is, then we convert the properties of the every clicked event, which targets the ad view, to a data dependency graph. We are building a data dependency graphs for future feature extractions. So this process of filtering involves around three steps. First, we check every of the app's permissions and filter out the uh, ones where there are no permissions. So we need certain amount of permissions to make sure that it's related to mobile ads. Second, we use an obfuscation resilient tool to detect third parties libraries called libradar. So basically, these are libraries that uh, aid in discarding apps that have no uh, interest with ad libraries or connection to ad libraries. And third, we actually try to remove any views that have no uh, link to ad views to avoid any unnecessary analysis. So only after these three steps, we perform the static analysis. So now coming to the static analysis, we use tools like Soot and FlowDroid to build the interprocedural control flow graphs or ICFGs. We also use the diffuse, the DUs or UDIFs or UDs routes to build relevant chains. So these three graphs individually cannot represent the prior parameters uh, assigned to the motion event.obtain function, and the trigger condition uh, processed of the dispatch touch event. To alleviate this, what we use is a data dependency graph to show an overall properties and trigger conditions of the click event. So in a DDG, we have a node that equals the statement and an edge that replaces the dependency between the two nodes or the two statements or functions. So with this, we build a backwards program where we input the ICFGs, the DU and UD chains as the root, and the display touch event and parameters of the motion event as as those two as the root. So after building our DGG, we move on to the feature extraction module. So after we build the DGG, we actually try to find which of the features are used to actually verify a human attack, whether what actually to select to know that whether a human attack happened or not. So what fraudulent apps do is they actually obtain features like the height, the width, the view of the ad. They also construct fake clicks coordinates following a random distribution, which tries to mimic a benign app behavior. So what we do is we try to run the model through around 7 features to find the relevant feature vectors. So going through the 7 features, the first one we'll start with is the access API, which is it involves fraudulent apps getting the coordinates of real users. As example, the get x and y, the x and y coordinates to construct the uh, coordinates itself. So the existence of such an API proves that there is a fraudulent application. Second is the number of APIs that are getting the size of the ad view or the view size API. So many fraudulent apps, they also try to obtain the size of the ad view in order to place the coordinates in the specific locations inside the view. Although benign apps also use this view size API, they use more frequently in fraudulent applications. So the third one is the number of constants, the const. So fraudulent apps, they try to click on the area around a fixed point in the view, ad view, such as the download button or the install button, and they will obtain the size of the view and calculate it with a constant to get the specific point coordinate. The fourth one is the number of APIs getting a random number or rand access. So if the API uses functions like rand access, it is very likely that it is a fraudulent application that is trying to generate random click coordinates for fraudulent clicks. The sixth is random numbers in condition expressions. What we do is the fraudulent applications tend to they randomize the clear trigger conditions or the trigger frequencies of the humanoid attacks. So here, dynamic analysis, the old systems, they require a lot of time and resources to actually to detect them, and it's actually very difficult to pull all paths that a humanoid attack pursues. The seventh is a system call in conditional expression of SYS API. Here that there's certain system properties or environmental parameters, example the OS or hardware traces, that can be exposed in an app through system interfaces. So what we see is human attacks. They clearly use the sys API far more than benign apps, and they use it to interact directly with the OS. So combining all these 7 features, we get our feature space for our experimental result. And we also try to apply a normalization on all these features so that to reduce the complexity. So now we come to the final stage, is the fraud decision module, where we need to specify for the existing modules, we have to specify many rules for the classification. This actually leads to very high false negatives due to incomplete and unrepresented views. This requires a large number of malicious samples for the training, which is hard to get. And this is the older terminology or the older dynamic solution. So what we have is if we have a lack of labeled datasets. To overcome this type of problem, we actually use veritational autoencoders or the VAEs. We train our datasets on them because it helps when we have limited positive examples to train our dataset on. So what we use is we use a benign examples to train our classifier, and we determine whether the input is benign or if there's a reconstruction error between the input and output. So what the encoder is, it is a neural network, and it features the vectors generated by the click scanner. And that is also the case with the decoder, which is also a neural network, and its input is representative. Here we can actually reconstruct the error to measure differences between the input and the output. So in the training stage, we train with benign examples to feature vectors in advance so that the encoder will be able to learn the representation of benign examples. Here we select around 10,000 benign apps, and we train the VAE with the feature vectors. So to conclude, the old dynamic way of actually solving human error attacks is it's very difficult to do. So what we propose here is the click scanner application, and this is used to actually uncover human error attacks. So it is what it is. It's based on static analysis and veritational autoencoders with actually a limited knowledge of the fraudulent examples. What Click Scanner did was they conducted an almost large-scale measurement of the app markets. They used around 120 apps from the Google Play and UI app gallery, and they were able to relieve certain phenomena where even if they use the top-rated 20,000 apps, Click Scanner was able to identify almost 157 fraudulent apps which had prevalence of human error attacks. Yeah. We also observed, the paper also observed that the majority of the human error attacks is SDK based. So they use mostly third-party SDKs. And right now, currently, human attack is the more dominant attack approach. Thank you.